Good morning. Okay, so thanks for coming. Okay, and so next week we will have our exam too. So we are combining the contents for this week and next week together and give the lecture summary now. So we are going to talk about a new series of lecture slides where we are describing some basic results in number theory. So we will start by talking about divisibility and greatest common divisor. And also, we will introduce the fundamental theorem of arithmetic. All these topics, you have actually learned this in the primary school. But somehow, we are going to look at it again and then give the formal proofs for why they are correct. And after that, this is going to be something that we want you to look at afterwards. Is we will talk about the modular arithmetic notation, and then we will talk about famous results by Euler, and so we will introduce something called the Euler phi function, which is used in the RSA crypto system. And the reference for actually the lecture notes here and the outline or whatever, they are coming from the course notes of an MIT online course by Professor Meyer and Professor Rubenfeld. Yeah, so this is what we are going to talk about. First of all, what is number theory? Number theory is the study of integers, and somehow for a long time, once it is thought to be of only for interest only. It doesn't have any application. And number theory has a lot of questions or a lot of results that are easily described, but somehow these results are difficult to show. And sometimes some of the results, maybe it's not results, some of the theorems that people believe are correct is still not proven, so it is kind of in a conjecture status. On the other hand, number theory problems are sometimes very hard to solve, and because it is difficult to solve, then people apply it in cryptography. Because in cryptography, we really want to have some hard problems so that the hackers cannot solve it very quickly in reasonable amount of time. So to begin with, so these are just some famous problems in number theory, and then we are not going to talk about this in the lecture because they are too hard. But somehow, let us check that. Maybe it is nice to know. The first one is the Fermat-Last theorem. So the theorem states that for any positive integers x, y, z, then there is no way that we can find x to the power n plus y to the power n is exactly equal to z to the power n when n is greater than 2. Now when n is equal to 2, we have numerous pairs. We have infinite triples of x, y, z that satisfies this formula. X squared plus y squared is equal to z squared. But on the other hand, x to the power 3 plus y to the power 3 is equal to z to the power 3. Are there integer triplets that satisfy this equation? The answer is no. This theorem was proposed by the French mathematician Fermat a long time ago, more than 350 years ago. But at that time, he didn't show a formal proof. He just wrote down this so-called theorem at the book margin. And after a long time, so after 350 years, then it is finally proven by an English mathematician, Andrew Wiles. So this is now a fact. And the other one is the so-called Goldbach conjecture. So Goldbach conjecture says every even integer greater than or equal to 4 can be expressed as a sum of 2 primes. So for instance, 4 can be written as 2 plus 2. They are all primes. 6 can be written as 3 plus 3. 8 can be written as 3 plus 5, and so on and so forth. Somehow, this conjecture is still not proven. Nobody knows whether this is correct or wrong. But so far, because nobody knows it is correct or wrong, that means that so far there is no counterexample yet discovered. The closest result that we have, this is one of them. So a mathematician called Ramer, he showed that every even integer can be expressed as the sum of at most 6 primes. So whether we can make this 6 into 2 is still a question, an open question. Okay, another problem. So this is called the twin prime conjecture. So are there infinitely many primes P such that P plus 2 is also a prime? So if it happens, then these two primes are called twin primes. For instance, 3 and 5, they are twins. Now, why do we call them twins? Because they are having a value which is very close to each other, just like the twins. We can't have P and P plus 1 to be a prime at the same time, except for 2 and 3, because for larger numbers, one of the value P or P plus 1 must be an even number. So in that case, it cannot be a prime. So the closest possible two primes will be at a difference of 2 or more. Okay, so in general, in this conjecture, we are claiming that we are suspecting that we can always have a prime P and P plus 2 that are both primes. And this result is not known whether it is correct or wrong, but then we have several results now. The first one is proven by Chen in 1966. So he says that, okay, there are infinitely many primes P such that P is a prime, right? And P plus 2 is the product of at most 2 primes. Okay, so either P plus 2 is a prime or P plus 2 is a product of 2 primes only. So it's like a pseudo prime, very, very close to a prime number. So this is one of the results that somehow closely related to this twin prime conjecture. And very recently, there is a mathematician called Zhang Yitang. He has proven that there are infinitely many primes P such that P and P plus, I forget the number, a very large number, such that it is also a prime. That means that the gap between the closest primes will not be very large if we consider primes P that can be as large as possible. That means that we will never run out of 2 primes that are close to each other. So this is what Zhang Yitang has proven. This is actually the first result that has given a proof about the distance between 2 primes, whether it is always possible to find 2 primes that are close enough to each other. And after Zhang Yitang's result, then a group of mathematicians further improved this so that now we can be sure that we can always find 2 primes such that P and the next one is within distance at most 246. Okay, so this is a result proven by a group of mathematicians including Terence Tao. Okay, another famous problem is the primarity test. So the question asks, is there an efficient way to check if n is a prime or not? So we know how to check if n is a prime or not. We have written this as our fundamental exercise in programming. So we can check whether 2, 3, 4 up to n minus 1 can divide n properly. So this is a method. But this method is not fast in the sense that it takes exponential time to compute. Although we can see that, oh, the given number is n, and then we take order n operations. But somehow, to describe this problem, we don't need order n bits to describe the problem. We need log n bits so that we can describe the problem nicely. Because to describe the problem, any efficient way to check if n is a prime, any efficient way, blah, blah, blah. So all these are something that is constant. It does not depend on the size of this input. And the input itself, n, can be expressed using log n bits. So in that case, the problem size is only of order log n bits. When the problem size is only of log n bits, an algorithm that runs in order n time is an exponential time algorithm in terms of the input size. So the usual way that we check whether n is a prime is an exponential time algorithm. So one question here is it possible to design polynomial time algorithm that runs in log n to the power constant so that we can check if n is a prime or not? And then this result is proven in 2002. It says that yes. So the three Indian mathematicians, Agarwal, Kayal, and Saxena, they have given an algorithm that runs in log n to the power 12. So this is the input size to the power constant. So this is a polynomial time algorithm for solving this. And this algorithm only returns yes or no. Yes when n is a prime, no when n is not a prime. So when n is not a prime, this algorithm does not give you any factor of n. It just tells you that n is not a prime. Okay. So primary testing is sometimes confused with the other problem called factoring. So factoring is I give you a number n. Can you return a factor of n to me? A non-trivial factor, except 1 or n. So in particular, the simplest case will be I have a number n, and then it turns out that n is a product of 2 primes. Is there an efficient way that you can tell me what is p and what is q that constructs this n? So far, there is no known polynomial time algorithm. So again, if you want to have a polynomial time algorithm, the running time should be log n to the power constant. So the best algorithm that we have here is e to the power something like this, and then this is smaller than n. So it is somehow this is still an exponential time algorithm, but not that exponential. It's not like n. So far, nobody knows whether we can solve the problem here using polynomial time. Okay, so these are all the introduction of some famous problems that we have in number theory. So now we go back to our primary school knowledge. Okay, so we first talk about divisibility. Now in this lecture, when we talk about number theory, unless we have a special case, so we will assume all the variables are integers. Okay, and then we introduce a notation. This is the notation. So this notation says A divides B properly. So when we say A divides B, it means that there exists an integer k such that A times k is equal to B. Is that okay? So for instance, 7 divides 63 properly because 7 times some number, some integer, is equal to 63. And indeed, every number, so make sure that you understand this, every number divides 0 properly. So A divides 0 for any A except A is equal to 0. So we don't, yeah. So this is a special case. Any non-zero integer divides 0 properly. Okay. Now, if A divides B, then we will call B is a multiple of A. So this is just some notation, some description. And what is a prime? A prime is a number, a positive number greater than 1. First of all, it doesn't include 1, okay? A number greater than 1 and such that only 1 and P are its factors, okay? It doesn't have any other positive divisors, positive factor, then it is called a prime. and every other number greater than 1, it is called a other number, which means that every non-prime number greater than 1, it is called a composite number. So primes are this list of numbers 2, 3, 5, 7, 11, 13, 17, 19, and so on and so forth. And the remaining numbers except 1, positive numbers except 1, 4, 6, 8, 9, 10, 12, and so on and so forth, they are composite numbers. Okay, now we have these lemmas. Okay, so notation here, a divides b. So it means that there exists an integer k such that ak is equal to b, right? So it says that if a divides b properly, then a divides b times c for any integer c. The other one is if a divides b and b divides c, then a divides c. Okay, so these are somehow some knowledge that we have known since our primary school days. The next one is if a divides b and a also divides c, then a will divide any linear combination of b and c. Yeah, because a divides this part, a divides this part, so overall things a will divide. And the fourth one is suppose that c is not 0. Then we will have a divides b if and only if ac divides bc. Okay? So all this can be proven using our definition of this notation a divides b. Okay, so I will leave this for you to check. Okay. And the next one is the so-called division theorem. Then we have also known this for a long time. So what does it say? So here, suppose that we have an integer n, and then we have an integer d, where d is some integer greater than 0. So when we try to divide n by d, what will happen? Then we will have a quotient part and the remainder part, such that n can be expressed as q times d plus r, where r is the remainder part, and then r is some number always between 0 inclusively, but less than d. Okay? So for instance, if I divide 5 by 2, then I will have a quotient 2, and then I will have a remainder 1. If I divide 100 by 3, then I will have a quotient 33 and the remainder 1. And then if let's say I try to divide minus 4, okay, wow, this is somehow something difficult. Minus 4 by 3. Then what will happen? Then I will have a quotient of minus 2 and the remainder of 2. Okay, so it says that when n is divided by d, then we can have a quotient and a remainder part, such that the remainder part is in between this range 0 and d. And what's more is, such a pair of q and r is unique. To show why this is correct, then this is a unique existence and uniqueness theorem, okay, or statement. So usually we can show the existence easily first, and after we have shown the existence, we can show the uniqueness. Okay, uniqueness is usually shown by using contradiction, and here for the existence, we can show this by induction on n. So when n is a number between 0 and d, smaller than d, then this is correct. And then for any number that is okay, then let's say if let's say n is okay for all the numbers less than or equal to some multiple of k times d, or strictly less than some multiple k times d, then in that case, yeah, for any n such that it is less than k plus 1, this number times d, then it also works. So somehow this is easily shown by induction. Okay, so this division theorem, we know this already. We have applied this numerous times since our primary school days. But why it works, then yeah, this is good to know. Okay, now we have talked about divisor, right? So we will introduce the concept of greatest common divisor. So what is the greatest common divisor? Okay, so this is the easiest meaning of greatest common divisor. So first of all, a divisor of A is something that divides properly A. So a common divisor of A and B is some divisor that is both A and B. So some divisor that divides properly A and also divides properly B. And greatest common divisor are the greatest possible common divisor. Okay, and then this is written as or denoted by GCD of A and B. So some example, GCD of 12 and 40 will be 4. GCD of 5 and 18 will be 1. And in such a case, they don't have any common divisor greater than 1. So we call them co-prime. So the prime factors of these one are different. So we will talk about the fundamental theorem of arithmetic later. So but somehow these two numbers, if they have no common divisor other than 1, then we call them co-prime or relatively prime. Okay. Now GCD of any non-zero number with 0 is equal to the original number, that number. So GCD of 7 and 0 is equal to 7 because 7 divides 7, 7 divides 0. Okay, and it is the largest possible one. Oh, and for positive number here, I should say. So for instance, GCD of minus 7 and 0, this will be 7. Okay. Now we have a very interesting theorem related to greatest common divisor. It turns out that greatest common divisor has another property that uniquely defines it. So the greatest common divisor of A and B is always the smallest positive linear combination of A and B. Always the smallest linear combination. So we need to be careful. We need to have positive. Yeah, because otherwise we can have linear combination of A and B that is going to minus of a very large value. And also, we can always have a linear combination of A and B that is equal to 0. That's easy. Yeah, because we take B copies of A and take minus A copies of B, then they add up to 0, right? So what we are showing here is there can be many different linear combinations of A and B, and we find the smallest positive one, and this is always equal to the GCD value. So for instance, GCD of 52 and 44, by using our primary school knowledge, we can compute it as 4. But then to see that this 4 can actually represent it as a linear combination of A and B, yeah, we can find out 6 times 52 plus minus 7 times 44. It turns out that after some checking, it is equal to 4, and then there are no other value, no other positive value that can be expressed as a linear combination of 52 and 44. Okay? So how can we show this? So there are different ways of showing this, but then let me describe a way that is described in the lecture notes of the MIT course. We are going to show these two facts. We want to show, okay, so suppose that M, we use M to denote the smallest linear combination of A and B. We don't know what it is, but let's say this must be there, right? I missed the word positive. Let M be the smallest positive linear combination of A and B. Yeah, I should add the positive one. Okay. I don't know what it is, but then we want to show that M will be greater than or equal to GCD of AB, and then also M is less than or equal to GCD of AB. Then the combination of these two will make M to be equal to GCD of AB. Now we are going to show the first part. Okay. So we want to show M is greater than or equal to the GCD of AB. Now, what we know here is by the definition of a common divisor. So GCD of AB itself is a divisor of A. So it divides A. And so it also divides B because it is a common divisor of A and B. So it divides B. Now we have proven before that if something divides A and something divides B, then something divides any linear combination of A and B. So that's why we have GCD of AB will divide M. Is that okay? Now if GCD of AB divides M and both of them are positive, right? So it means that GCD of AB multiplied with some constant k greater than or equal to 1 will be equal to m. So in that case, m must be greater than or equal to GCD of AB. Is that okay? GCD multiplied with something greater than or equal to 1 is equal to m. So the smallest possible value of GCD multiplied with something greater than or equal to 1 is GCD AB. So that's why m is always greater than or equal to GCD of AB. So we are now here. We have shown that m is greater than or equal to GCD of AB. And the other part is we want to show that m is less than or equal to GCD of AB. And for this one, we are going to show this by contradiction. Okay, so let's see whether let's see whether it is contradiction or what. But let's see. Okay. So suppose that we want to show this, right? What we are going to show here is we first show m is dividing a. And after we have shown m is dividing a properly, then by symmetry, we know that m must also divide b properly, right? And if these two happens, then m will be what? M will be a common divisor of a and b, because m divides a, m divides b. By the definition of greatest common divisor, so it is a common divisor that is greatest. So in such a case, m must be less than or equal to the GCD, because m is a common divisor. Okay, so what we need to show here, all remains to show is m will divide a. Okay? Okay, so we are using the division theorem to help us. So let's see. We don't know whether m divides a or not. So let's try to divide m. Let's try to divide a by m and see what will happen. Okay. So we have a can always be written as some quotient q times m plus r. This is about dividing by m. So this r will be in between 0 and m. R can be equal to 0, but r must be less than m. Now we recall that m itself is what? M itself is the smallest linear combination of a and b. So m itself can be written as s times a plus t times b for some s and t, right? Because this is meaning a linear combination of a and b. Now we substitute this m here. We will have a is equal to q times sa plus tb and then plus r. Is that okay? And then after we rearrange the terms, we will have r is equal to this one plus this one. Is that okay? And what do we have? R is a linear combination of a and b. But r is less than m. And m is the smallest positive linear combination of a and b. So what's going on? So it means that r cannot be a positive number, because if r is a positive number, then m will not be the smallest positive linear combination of a and b. So this means that r has to be 0. Okay, now r is 0, then we get back here. R is 0, so what does that mean? It means that a is equal to q times m, so m divides a. That's done. Okay, so we are not proving it by contradiction, so I'm sorry about this. But then we can formulate this by proving in another way, so that we are showing this by using proof by contradiction. But this is a direct proof showing that m must divide a. Okay, now because m divides a, we have shown here m divides b, and m is a common divisor, so m must be smaller than or equal to the greatest common divisor. Okay, that's it. Now this is an important result. So that means what? Greatest common divisor has two different property. One is we can view this as a common divisor of a and b, and it is greatest. And also the other part is it is the smallest positive linear combination. Okay, and because of this, then we can somehow show a couple of results here. So for instance, every common divisor of a and b divides GCD of AB. So this says that it is not just the largest common divisor. It is also something that other common divisor will divide. Okay, so it's not just small and large property. It is always the smaller divisor always dividing the greater divisor. Is that okay? The greatest common divisor is always properly divisible by any common divisor. Okay? And then GCD of KA, KB, you can take this K outside and it is equal to K times GCD of AB. And then if I know that AB, they do not have any common divisor, so GCD AB is equal to 1, and somehow we know that A and C do not have any common divisor, so that GCD of AC is equal to 1, then even if we multiply B and C together, we get the number BC, then A and BC do not have any common divisor other than 1. So GCD of ABC is equal to 1. The next one is, suppose that A divides BC, but then we know that AB do not have any common factor. So GCD of AB is equal to 1. Then A must divide C. And finally, GCD of AB is always the same as GCD of B and then A ram B. A ram B is when A is divided by B, what is the remainder? Okay, so this is, so in a programming language, it is A mod B. And this part is exactly the reason why the Euclidean algorithm to find the greatest common divisor of AB works correctly. Yeah, we start with finding the greatest common divisor of AB, but instead, let's say A is the larger number, B is a smaller number. Instead, what we are going to do here is that we replace A by A mod B, and then find the greatest common divisor of the resulting two numbers B and A mod B. So we are making the problem into from two large number A and B into two smaller number B and A mod B. Is that okay? So in such a case, the number that we are considering will be getting smaller and smaller. So eventually, we will be able to solve the problem and finding the greatest common divisor. Okay, so we can prove everything using the theorems or the lemmas that we have derived so far, and without using any extra knowledge, like there is a unique way to factorize a number into primes. So we don't need. So for instance, let's see how we prove 3. Okay, theorem 3. Okay, so the point 3 here says, suppose that GCD AB is equal to 1, GCD AC is equal to 1, then GCD of A and BC is equal to 1. How we can show this? Okay. Now, this one turns out to be easily shown if we know the property here, the smallest positive linear combination of AB property here for a GCD. So because GCD of AB is equal to 1, there exists S and T such that 1 can be written as a linear combination of A and B. So 1 can be written as SA plus TB. And similarly, 1 is a greatest common divisor of A and C, so there exists U and V such that UA plus VC is equal to 1. We have this one, we have this one, so we can multiply them together, we get it is equal to 1. And then after expansion and rearrangement of terms, what do we have? We can express 1 as a linear combination of A and then also BC. So what does that mean? 1 is a linear combination of A and BC. And 1 is actually the smallest positive number that we can ever imagine. So 1 will be the smallest positive linear combination of A and BC. So that's why GCD of A and BC is equal to 1. Okay? And then let's see 4. Okay, 4 says, if A divides BC, but then A and B does not have any common factor, then A must divide C. Okay, so let's see how we can do so. So first of all, A divides BC. This is given. But we also know that A divides AC, right? So that means that A must divide GCD of AC and BC. By statement 2 here, GCD of KA-KB is equal to K times GCD of AB. So in that case, this GCD of AC-BC, we can write it as what? We can write it as equal to C times GCD of AB. Okay. And then what is GCD of AB? AB are given to be having no common factor. So GCD of AB is exactly equal to 1. So what does that mean? GCD of ACBC is equal to C times GCD AB is equal to C times 1 is equal to C. So this number is exactly C. This number is exactly C. So that's why A divides C. Okay, so notice that we do not use any extra knowledge except for those that we have already derived. So in order to prove 4, of course, we will need to prove 2. So this is going to be left as an exercise for you. So this is not difficult. So you can show this easily. And lastly, let's try to prove the correctness of the Euclidean algorithm. Okay. So here we want to show that GCD AB is equal to GCD of B and A mod B. So let's see how we can show this. We use the same technique as before. We want to show GCD of AB is smaller than or equal to GCD of B, A mod B, and also GCD of AB is greater than or equal to GCD of B, A mod B. And if this is the case, then they are equal. Okay, so why is it true? GCD of B and A mod B is a linear combination of B and A mod B, right? But then if it is a linear combination of A mod B, then in that case, any common divisor will divide this linear combination. So in that case, GCD of AB, is that okay? GCD of AB must be dividing this properly, and so that GCD of AB must be smaller than or equal to this one. So we assume that they are both positive. Okay, so in that case, this one is smaller than or equal to this one. On the other hand, opposite this time, any linear combination of A and B, we can always express it as a linear combination of B and A mod B. So each time we see an A, we replace it by some quotient times B plus A mod B. So in that case, rearranging the terms, then any linear combination of AB can be seen as a linear combination of B with A mod B. So again, we repeat the argument so that we know that the GCD of B and A mod B must divide this linear combination. So in that case, this part, this GCD here, is smaller than or equal to this part. So done. So it is easy. Okay. Okay, so the most difficult part for this set of slides is why GCD can be having the property that it is equal to the smallest positive linear combination of the two numbers, and also why the Euclidean algorithm works. Okay, and we have a few things to talk about today. Yes, sorry for the delay for today. So we want to talk about a few more slides before we leave for today's class. So we want to talk about the fundamental theorem of arithmetic. Okay. So here it says that, so this is also a result that you have already known in the primary school. So we are claiming that any positive integer n greater than 1 can be expressed as a product of primes, multiplying them together. So if we arrange the primes P, P1, P2 as a monotonic increasing order, then this expression is a unique method. So for instance, the number 100 can be expressed as 2 times 2 times 5 times 5. And then there is no other way to express 100 as a product of primes, assuming that we are listing the primes from small to large. So for instance, the number 24 will be written as 2 times 2 times 2 times 3. Is that okay? And this theorem is called the fundamental theorem of arithmetic. Yeah, basic mathematics arithmetic to calculate, right? So why is it correct? Okay, in order to prove this, then we have some useful lemma. So this is the lemma that we are claiming. Suppose that P is a prime if P divides A times B, then either P divides A or P divides B. Now this is easily shown. Okay, the reason is that the greatest common divisor of A and P must either be 1 or P. Yeah, because the greatest common divisor of A and P itself has to divide P. And P has only two divisors, either 1 or P. So the GCD of AP must either be 1 or P. Now, if the GCD is P, then we are done, because in that case, P divides A. If the GCD of A and P is not P, then it is 1. Then by the result that we have just shown, P must divide B. Okay? The second part is a general version. Suppose that P divides a product of numbers. Then P must divide at least one of them. Okay? So this is the basic lemma that we have. And using this, we can show the fundamental theorem of arithmetic. Okay, we are going to show this fundamental theorem by using strong induction. We show that for any n, it can be expressed as a product of primes. N is greater than or equal to 2. So first of all, the base case is n is equal to 2. We are going to show existence first. There exists a way to express a positive number greater than or equal to 2 as a product of primes. We show existence before we show uniqueness. Okay. Now, inductive case is assume that all k less than n can be written as a product of primes. So from 2, 3 up to n minus 1, we know it is already done. But how about the case when we are looking at n, the number n itself? Now, there are two cases. N itself is a prime, then we are done, because n is expressed as n, so n is a prime, so we are done. On the other hand, if n is not a prime, then n can be written as a product of two numbers or more, right? And then each of these numbers has to be smaller than n. So we are not writing it as 1 and n, not like 1 times n. So if n is not a prime, then there must be some divisor of n, which is not 1, which is not n. So we have some divisor which is strictly in between 1 and n. So we call it a. So n can be written as a times something, let's call it b. And then these two numbers, we can easily check that because a is strictly between 1 and n, so b is also strictly between 1 and n. In that case, by our induction assumption, we know that a can be expressed as a product of primes, b can be expressed as a product of primes, so that's why n can be expressed as a product of primes. Okay, now we want to show uniqueness. So uniqueness, as we have mentioned before, uniqueness is usually shown by contradiction. So if the theorem is not correct, so that means that for some n can be written as a product of primes in different ways. It's not a unique way, it's in different ways. Then in that case, let's find out the problematic number n. And then if there are more than one, then we find out the smallest one that is creating the trouble. So we let n to be the smallest integer that can be written as a product of primes in more than one way. So in such a case, n can be written as p1 times p2 up to pj, and then it is equal to q1 times q2 up to qk. Okay, now we have the lemma in use now. P divides AB, then P divides P divides the product of things, then P divides something. Okay, so in such a case, look at it. And let's pick any prime here. Let's say P1 here. We know that P1 divides n because this is P1 multiplied by something. So P1 divides n. So P1 divides the product of these parts. So by our lemma, P1 divides at least one of the values here. And in particular, that value that we must have, because all these are primes, that value has to be the prime number P1 itself. So what do we have? So we will have P1 is equal to Qi for some I. And in such a case, then what will happen? So if we remove this P1 and remove that Qi, then we will get a smaller number, which is equal to n divided by P1, right? But then in that case, n divided by P1 is a number that can be expressed as a product of primes in more than one way. And we get a contradiction. we are saying that n is the smallest possible number, but now we get n over p1, which is not okay. So we have a contradiction. So we are done with the proof that the prime factorization is unique. Okay, so this is the end for this week and next week's tutorial. This class, we will have the tutorial of this part next Tuesday. So for next Thursday, the lecture summary will be replaced by the exam 2 solution. Okay, so that's all for today. Yeah, and then good luck. Yeah, good luck to the exam. Yeah, thanks. Okay, see you.